Hello. Quick show of hands. Who here uses CAD? There we go. All right, keep them up. Who else is a mechanical engineer? Okay. Um, uninstall SolidWorks. Thank you for coming to my TED Talk. Just kidding. Uh, Firstly, thank you to Benji for letting me do this. I care very deeply about this topic. I'll get into why here in a second. I'm going to try and get through this pretty quickly because I want to leave room for the Q&A. I'm pretty opinionated about this too, so I want to give you an opportunity to argue with me about that. So a little bit about me. I am a mechanical engineer by training. I actually got my degree in mechanical engineering. I got super lucky in my career, and I got to work for artists like Taylor Swift and Lady Gaga designing staging machinery and stuff, which was very fun. And then I ended up, by way of doing that, working at the Macy's Thanksgiving Day Parade. I got to build out that engineering team, and then I pivoted into tech. And that's when I got to most recently design or help build and design some of the rear sensors for the iPhone 17 Pro. So now I'm at work. And so I built work because I noticed something really important, and it didn't matter if I was designing a 4-part weldment or if I was designing an iPhone. What I learned was every engineer in every one of these industries has the exact same problems. And it's usually, well, you all know, so I'll leave it there. But let's talk about that. That's the topic for today. So my key point, or the key thing that I sort of believe, and it's driven my work at work, and it's really driven a lot of the way I think about this, is I truly believe engineering is art. And that's not marketing speak. I truly believe this. I think engineers understand this fundamentally. And so this presentation, I want you to learn 2 things. I'm going to make 2 points. But remember this, engineering is an art thing. I think that's really important. So let's start with engineering software back in the 60s. So this is the SR-71 Blackbird. The SR-71 Blackbird. It started design in roughly 1957. It was a reconnaissance aircraft developed by the Lockheed Martin Skunk Works, if you've heard of this. They were kind of like a rogue outfit that did essentially the most advanced engineering the world had ever seen. We haven't heard much else from this era that was as impressive as this. But the reason I'm bringing this up is because this was done before CAD. So this is the assembly line for the SR-71. So here's some fun facts about this. It traveled at 2,100 miles an hour. So to put that in perspective, you could go from New York to London in less than 2 hours. They finished this in 1962, their first prototypes. So just more than 50 years ago, they figured this out. This is incredible. I'll tell you one of my favorite stories about this. This is such an impressive engineering feat. At speed, it was so fast that it generated so much heat around the fuselage, 1,000 or more degrees Fahrenheit, that it would actually expand. And so to make it work at speed, they actually had to design it to be smaller on the tarmac. And so when they went to fuel it, it would literally leak. So you would fuel the aircraft and then speed run getting it into the air before you ran out of fuel. This is the level of engineering that was going on in 1960. This blows me away. And they did it without CAD, or FEA for that matter. So this is how we did it. We put men on the moon. We won the Second World War. We figured out flight. We did all of that before CAD. And here we are today trying to get our constraints to not break in SolidWorks. So I'm making this point because I think there's something really important for us to take from this. I think we used to do engineering as art, and something happened right around this time when we started to take away the artistry that draftsmen had, because I think it went down the stack. So I'm going to give you another sort of fact about that plane. In 1962, Soviet physicist Pyotr Ufmetsev published a radar diffraction paper called "The Method of Edge Waves in the Physical Theory of Diffraction." Say that 10 times fast, I dare you. This was translated by the U.S. Air Force and then later used in the 1960s and 70s by the Skunk Works at Lockheed Martin. Engineer Dennis Overholzer used this to mathematically model radar reflections. And this is what made the SR-71 invisible. By the way, it was invisible. It also at Mach 3, but it was also invisible, 1960. So why am I telling you this? This is a room full of computers. If your job was to do math, you were literally called a computer. And computers replaced computers. And so the Russians published a paper about how to make aircraft invisible. They didn't realize what they were doing because they thought it wasn't very useful. And then Dennis at the Skunk Works realized, well, wait a second. We just replaced them with this mainframe and it does computation super fast. It's like having thousands of these people. What do we can do with that research paper? And then we won the Cold War. So the point I'm trying to make here is that computers replaced this room of people. Let's go back a slide. Computers did not replace this room of people. The mechanical engineers here understand this. Where did this room of people go today? The answer is, some people at Draft are smiling at me right now. It's the engineer. So we traded a room full of skilled artists and we forced engineers to do their work instead. So that's where we are today with computers. Computers replaced this room and empowered engineers and then forced this job on us. Remember, engineering is art. So I would like to introduce you to text-to-CAD. This was invented about the 16th century. It's a room full of draftsmen, and the engineer here is using text to convey CAD. You see where I'm going with this? Okay. So this paradigm has existed. We know this. And yeah, we're kind of going back in time to get back to this, which is interesting. Note that text-to-CAD in this was actually not sufficient. She's using paper and books and pens and rulers to convey intent. So what does this mean? I don't think Dennis today would have been able to find the time to perfect his art of engineering and to read the research papers that led to us winning the Cold War. My point here is I think computers and software haven't really helped mechanical engineers in a way. And it's kind of sad. Because if you look at the manufacturing industry, for instance, Jim at Sen is spinning out parts per machinist more than anyone else. And it's because the software is enabling that. And I don't think that's true for mechanical engineers. So, where do we go wrong? This is Ivan Sutherland. This is at MIT Lincoln Laboratory. 1963. Note that is not a computer mouse. That is a pen. So the first attempts at getting computers to be useful for mechanical engineers, I think, started in the right sort of path. It was, hey, we have paper and pencil. Why don't we just keep doing that? By the way, this thing was nuts. It actually had constraints. So this was a 2D sketch solver with constraints. Insane that in 1963 they were doing this. And it wouldn't be until maybe 20 years later that we actually got really useful CAD, but still, this was a pivotal moment. And so initially, computers made sense, and then they didn't. So what happened? It essentially goes back to this. This is the downfall of mechanical engineers. I know that that's a grand statement, but follow me here. This is the Xerox Alto. It was developed at Xerox PARC, and it was a prototype essentially for what became the desktop computer. The reason why this was bad news for us wasn't because of the keyboard. As you all know, engineers love numbers. Plenty of numbers on that thing. That wasn't the problem. The problem was the mouse. So we got away from truth, which was a pen and paper sort of way of working about things. And then we went to this. Now, the problem is that we don't necessarily think in terms of a computer interface, right? And when you think about the way that CAD works today, it's really just mimicking what draftsmen were doing 50 years ago. We haven't really evolved past that. I do want to give out a quick shout out. The best example of this today, I think or the best example of getting around this today is by a company called Shaper 3D, and they actually have a great iPad integration, which is Chef's Kiss. It's the pen, it's just fantastic. And if you don't believe me on this, consider this. In competitive gaming, like PC gaming, they've actually banned pointing devices like this from the leagues. And it's because it's so useful, it's so good. And the reason is because a computer mouse it's a relative positioning versus a pen is fantastic. You point to the thing, it's absolute positioning. And so we figured this out when we created the pen, and so we really haven't gotten far away from that. Just look at your phone. So, I just told you about the history of CAD software. Hold on, this is going to make sense in a second. So this is from, I'm sure some of you know this, Space Odyssey 2001. I love this image because I think this is exactly where mechanical engineering software is today. I'm seeing a lot of very confused looks. This is bringing me great pleasure. Thank you. All right. So what am I trying to say here? So in this scene, essentially, well, I'm not going to write. You've got a space capsule. You've got this sort of antiquated room that's kind of futuristic with the lighting. It's kind of confusing. It's kind of jarring in a way, but oddly beautiful. That's where we are today. That chair is Excel. That bench is code, and the bed is CAD, and it's just this old scene, and it's very confusing, I think. And here, the capsule is AI. So the computer scientists have given us one of the most revolutionary pieces of technology. And when I look at what we're doing with it today, I think of this scene, because we have these antiquated tools from the 60s that haven't really evolved, and we're trying our best to make it work. And I think we're going to need a stepwise improvement to get out of this room. So those are really my 2 points. The first point is, the tools haven't really served us. And I think this is the next point that I want to make. And I think everyone in the room who's developing engineering software should take this to heart. It's going to be a little dramatic, but I really do believe this. I think that solving this problem is one of the most consequential things we have to do as humans. And I know that this sounds woo-woo and everything, but you got to follow me here. I think that there's a world of abundance ahead of us. We're going to colonize planets and cure diseases and make machines that rattle really loudly. These are very important things, but it's true. And I think that the tools today get in our way, and they prevent us from sort of perfecting our art. And so I want you to ask yourself this question, and that's, consider that tools have made us more productive, but not increased our quality. Consider that we now do the work of 10 draftsmen, but we do the work of 0 engineers. And so what I'd like to do is bring us back to that art and perfecting it, and see how much quicker we can get to that future of abundance. It's not a matter of if. It really is a when. And so the question should be, what are the decisions we can make today to make sure we accelerate towards getting out of this room? And so whenever you're thinking you're doing B2B SaaS, you're actually doing something that's super, super important, and you should take it seriously. So thank you.